Okay, all right, so finally in Unit B, so we are out of the kind of introductory material and now sort of focused on, we can actually get into the kind of details of discrete event system simulation. So just a couple of reminders, there is a Canvas activity that is due before lecture B2, which is the next lecture. Again, there's, I think, 12 of these assignments, and your lowest 7 are dropped. You only have to do 5 of these throughout the semester. So you don't feel like you have to do all of them, but they're meant to help you sort of keep up with the reading and the topics as we go. Lab 2 is already available. So Lab 1 was a lot like the first part of homework B1. You're sort of coming up with things like entities, activities, etc. Lab 2 is a little bit like what we'll start talking about today, actually hand simulating through discrete event system simulation with some process logic. So, so Lab 2 will help you with the second part of homework B1. So likewise, if you're having trouble working through Lab 2, some of the resources for homework B1 might actually be helpful and vice versa. Homework B1 is technically released today, but it's been available on Canvas. The due date is on Canvas. I think it's roughly a week and a half, 2 weeks from now or something like that. It's just 2 questions. The first question is going to have you do a lot of the kind of Lab 1 things, gives you 3 systems, asks you to name some things, some possible entities, et cetera, that'll go into them. Then the second part of it has you walk through about 6 or 7 lines of a hand simulation with me giving you some timing stuff ahead of time that you can do. And we'll learn today, and we'll see more about that on Thursday as well. So, and then likewise with the labs, again, the TA should be available during the lab period if you need help with the hand simulation or just the general setup of the lab. But if you feel like you're pretty comfortable with the lab, then there's no attendance for the lab. There's also no sort of Zoom attendance as well. So the lab is really meant to be there. It's almost like a Flitz classroom where it's meant to provide you help on these assignments and not, extra lecture material. All right, so other things that are sort of extra here is that there are every semester that IISE and Rockwell has an arena competition where they've got some monetary prizes for first, second, and third for folks who build an arena model based on their prompt. This is always an opportunity for you to do for your final project. If you're, I'd say a majority of people do their own final project and don't worry about this, but if you're looking for something that might be a little more challenging, a little bit where you might be provided a data set that's complex, then this is a good one to look into for that. And so the deadline to enter is, I think, the end of September, so like September 30th, something like that. So if you're interested in doing that, then you should consider registering before the end of September. If you want access to Arena, it's available on the Brickyard 214 computers in person. There's also remote access available. This semester, there's 2 ways to get access to Arena remotely because they're testing out this Porto virtual system, but they've also got kind of the old system, which is remote access into 2 resources. And if you've got a Windows machine or a Windows emulator on your Mac or Linux, then there's a free student version of Arena, which you can download and use. And I've got instructions on how to do all that at this Arena downloading finding helpful example page on Canvas. So if you just go into the Arena help module on Canvas, that's like the first link. So we'll help you get there. We won't need Arena until I think Lab 4 or 5. So we still got a couple of weeks until we actually drill down into Arena. But if you're thinking about ahead, or if you want to sort of evaluate whether you want to do this, then that's there are other competitions every semester. So IISC also joins together with FlexSim. FlexSim is a competitor, competing product with Arena. The people who originally built Arena also built FlexSim. And so they left Arena and they started FlexSim. So FlexSim was kind of like an Arena 2.0. And so they have their own discrete event system simulation competition every semester, but it's always focused on kind of healthcare. So if you're interested in a competition-based sort of motivation to learn about DES, and you're interested in healthcare systems and healthcare OR, then this might be something to look into. Similarly, it's got monetary prizes and so on. It also has entry forms due at the end of September. So because it's administered by IISC, the same person at IISC is responsible for administering it. So if you contact Bonnie Cameron, she can tell you about both programs. And there actually are a bunch of others too. So another competitor to these two things is Simio. And Simio also has an annual competition that you can take a look at if you would like. And there's, I think this is, and so you can look into that. So if you're looking for something out of the ordinary, then these competitions, I'll remind you of these probably about until the end of September, just because of the deadlines, but they're not required. The final project that you'll do in this class, you can do on your own, doesn't have to be prompted by a competition. I just want to give you the opportunity in case you want to double dip and sort of use your efforts maybe towards some of these prizes and all of the fame and fortune that comes with it. Okay, so any questions about assignments, timelines? Questions online? Let me double check that there's, pull up the anonymous questions here. Okay, great. All right, so last time we started to introduce DES system modeling, discrete event system simulation. So we talked about in discrete event systems, the system changes its state only at discrete instance of time. This is very different than modeling like a baseball that's flying through the air. That baseball is constantly updating, it's continuously updating its state. If its state is its position and its velocity. The position of the baseball and the velocity of the baseball is, excuse me, over a smooth period of time is being updated. We're focusing on systems where we only worry about them changing at discrete instance of time. And so if you were talking about, again, a classroom like this, then someone entering the classroom changes the state of the classroom because the classroom had X many people in it, now it has X plus 1 in it. So it's those instants of time, those discrete instants of time that make these discrete event system simulations. And those, since the state changes, we call those events. And the time is going to, as we'll see today, time jumps from event to event, skipping everything in between. In the physics simulation of the baseball, as it's flying through the air, we care about all of the time from when the baseball was tossed to when the baseball lands, and every single part of that real line in between. In this case, we only care about things that happen in from event to event to event. Anything in between events, we assume nothing happened. The system just sat there and nothing changed. So we're just keeping track of these jumps, and we'll see exactly what we mean by that. As a consequence, these systems are said to be process-centric. So I'm going to use the term process a lot. You'll see process used in an arena a lot. The idea here is it's not like an agent-based model where you have an agent like me walking around making decisions on its own. It's more like you've got these individuals, which we'll define as entities here in a slide here, they're modeled explicitly, but they're passive members that are being shuttled around by these processes. So an entity goes through the process of, an check, and that entity requires an X-ray scanner in order to go through that process. So it's the wait for that resource. And then once the check finishes, the entity is shuttled off to the next process in the system. So the entities are being shuttled around by processes. They're not moving themselves, they're being moved by the system. It's like a big conveyor belt that's moving them around. And that's kind of what we're saying here. That's the difference between these systems and the so-called agent-based modeling that kind of we introduced very briefly and that you'll see again in lab 4. So as you know, in lab 1, and if anybody reading ahead, there's these entities. Those are our focal objects that flow through our simulations. So these are the things that are entering our systems and are exiting the systems, and we keep track of how long it took for them to go through the system in different spots. So they're passive objects acted on by processes. We can have different types of entities. We can have at a restaurant, you might have telephone orders, or you might have in-person orders. You might have other sorts of entities that might arrive, might be delivery agents who arrive. And so you might have, again, telephone orders, in-person orders, delivery agents, and all three of those things could randomly, arrive, and you'd have to process them in different ways. And that's going to affect the resource utilization inside the restaurant. If somebody who's handling the cashier now has to receive a delivery, then they can't take any in-person orders. But maybe the mobile orders can continue to go on because that doesn't require the cashier. So it's the resources are going to couple all these processes together where multiple can make use of the same resources, and entities might show up along multiple processes in parallel. So we'll see more and more of what that we mean by that. But entities are the things that are flowing through the system. They usually represent real, tangible things like parts in a manufacturing system, customers in a grocery store, students in a university. But we can also have these sort of fake entries or entities for modeling. We'll see maybe later in the semester, but it's this idea that if you're modeling, let's say, for example, a stoplight, that stoplight needs to change from red to green and back to red with a particular timing. Well, in order to implement that timing, we can create a virtual entity, which is like a little hamster that is going to be stuck in different portions of its maze for different amounts of time. And whenever it passes different portions, it causes the stoplight to change. So we can instantiate a single entity who just keeps moving from one point of a simulation to another and gets delayed at different time points, which represent how long the green light stays green and how long the red light stays red. And whatever it and allows to move to the other portion, we would change that light. So we can create these virtual entities which don't actually exist in the real world. We just have to create them for ease of use and modeling. But for the most part, almost all the entities we have are things that are moving around in the real world. Although I'll show you one counter example to that, which hopefully is an exception that proves the rule. And that'll happen here in a second. Now, I said they're going to have different types of entities, but among the same entities, we can have different attributes. And so a student may enter the room at 5, but another student may enter the room at time 10. We might stamp them with their arrival times so that when they leave, we can easily calculate how long they've been in the classroom. So we can stamp them with things that have to do with when they've arrived at the system, or we can stamp them with some more fundamental differences, like this person is an industrial engineering major, this person is an engineering management major, this person is from WP Carey. So all of those attributes may change the way they're handled downstream in the system. So common ones here, like I said, arrival time, due date, color, these are all things that ride along with each entity. So it's not a property of the whole system, it's property of an entity. When that entity leaves, those attribute settings kind of leave with it. And they can be changed during a simulation. So it might be that you have to increment how many times this modeled individual has gone through the scanner. And they might have to go back through the scanner and be able to keep track that this person's gone through 18 times through the scanner. So maybe we need to prioritize them over someone who's only gone through once because we need to get them out of the system. Attributes can change, but attributes ride along. They're members of the kind of data structure that is the entity. And then entities compete for resources. So, so this idea here, and these items are coming up because of an issue with how this PDF was rendered. So on the online version, I'll get rid of these weird items that happen to pop up here. But so these resources are required to perform an activity within a process. So like I said, if you go into an X-ray scanning process, every one entity needs to temporarily grab one X-ray. Once that process is over for that entity, then it frees up the X-ray machine for the next entity, and so on. So it's competition for these resources that restricts the flows of entities and causes them to wait. So examples of limited resources are people in stores, like clerks, support representatives, equipment, like machines needed to assemble things, computers, and even space. So the seats that are available for someone to sit in. So if there's no space available, then someone has to queue. And so that is a resource there. So within a process, entities, we say, seize a resource, and when they're done with it, release it. So when a resource becomes seized, it's like its capacity temporarily goes down by 1. and it's unable to be used by another entity. And then when that resource then gets released, it's like its capacity goes up by 1, and then now another entity can come and resource it. So it's almost like the resources are temporarily assigned or owned by the entities, but the entities flow through and the resources stay there. So examples, a table with 4 seats, an airline with 4 identical counter agents. So I mentioned that one here is that these are examples that have several units of capacity. So I can have in Arena, I'll end up, instead of creating 4 resources for seat 1, seat 2, seat 3, and seat 4, I will create one resource called seat, and I will give it a capacity of 4. And that just makes it easier to program. And so in the real world, we might view the resources discretely, but in a model, we often will just bundle them into a type of resource and then say how many of that resource we have. And so when I use the word capacity, think of that as a how many. How many of this resource do we have? And then if I use the word utilization, it's of my capacity, how many am I currently using? So if 2 people are sitting in the 4 seats, then I'm at 50% utilization, which hopefully these are terms that I'm pretty familiar with through some of the other kind of IEOR courses. So a number, and this number of units of resource or the capacity can actually change during the sim. So during the sim, we can simulate a machine failure. That might mean reducing the capacity by 1 for that resource. Or we can simulate more clerks becoming available because it's just during that time of the day, they've scheduled in more personnel. So capacity can change during the simulation, but we don't view those resources as arriving and departing. They're not entities. It's almost like they're always there. They're just refused to handle more entities until you increase capacity or decrease capacity. So resources are fixed, entities are flowing, but resources can have capacities that change over time. So any questions about that, about those 3 concepts, entities, attributes, and resources? Before I push the model a little bit here. Okay, questions online? Okay. All right, so I mentioned just a second ago that entities almost always move through systems, but there can be exceptions to that. Entities will always move through the computer model. In the world, sometimes it's actually convenient to think about things that are stationary as the entities. And here's an example of that. So take, for example, a vacuuming robot like this iRobot Roomba here. It has a bunch of different things that it can do. It could linger at different points in the room. And you can imagine that you might want it to make smart decisions based on what it's encountered. So if it's encountered a lot of particulate sizes, it maybe wants to do one thing. If it's encountered maybe wet messes, it might want to turn on a mopping unit. There's a bunch of different things it could do based on what it's encountering out there. So it could make decisions based on that. Now, this robot is moving through the system. And so when I think about how am I going to model how well this robot is working, I'm tempted to call this an entity because it's moving. But if you really think about it, even though the robot's moving, it's the thing that's always there in the system, whereas the things that are arriving and departing dirt that it's vacuuming, cleaning up. So I need to change my perspective and not think about the robot as the moving entity. I need to put sort of a reference frame as if I'm sitting on top of the robot. Now, if I'm sitting on top of the robot and modeling the rest of the world, it's not like the robot is finding dirt. It's more like the dirt is coming to the robot. And so it comes in the front of the robot makes a decision about the dirt, and then the dirt leaves the robot's view. So it's almost like it leaves the system. So in this particular case, if we think about ourselves as moving in the reference frame of the robot, then we have a stationary resource, the robot, and we have entities that are transient, the dirt that the robot encounters. So, so that's kind of an example there where it's more convenient to model the stationary dirt as entities. So if I want to build this in Arena, rather than building an agent-based model where I've got to actually simulate a robot moving around the room, I can create a resource in a stationary processing arena called, just, vacuum or something like that. And then I can create entities which represent the difference of dirt that the robot is going to encounter, as if the different types of dirt show up, where the frequent type of dirt shows up more frequently, the less frequent type of dirt is less frequent, and so on and so forth. And so that's kind of an example there where it would look a little strange in the computer model relative to what's going on in the real model, but it is far more convenient to fix the resource that's moving as if it is a stationary resource and animate the stationary entities. Does that make some sense? And maybe another application here will help out with example. So like as an example here, so this is some work that I have done in the past with building algorithms for making decisions in uncertain environments. Those algorithms which could be deployed in military applications, on autonomous helicopters, in sort of food delivery, humanitarian things, and undersea sea exploration. And all of these things were modeled after thinking the way predators make decisions about which prey to encounter. So in this case, this is actually also a predator as well. It's the bobwhite quail, very similar to the Gambel's quail that you see running around Phoenix. And so the idea here is, we need an algorithms that help decide how quickly do you move around, which objects do you pick up, which objects did you ignore because there's more valuable objects that would be a better use of your time, and so on and so forth. And so we modeled the decision making that happened in these animal systems as if these animal systems were stationary objects where the prey were coming. These are not sit and wait predators, but we modeled them as if they were. And then in doing so, we built algorithms that we implemented on moving resources, even though in the math, they were stationary resources. And we've even done that then with flexible manufacturing systems, where you can think about these conveyor belts are moving around and making decisions and so on and so forth. And because they're flexible manufacturing systems, sometimes it's not the entities on the conveyor belt moving from machine to machine, it's sometimes the machines moving entities. And although we want to model, where should the machine move next, it ends up being more convenient to build a model inside the computer or inside the math as if the machine is stationary and the entities are arriving at the machine. So this is just an example where, although generally speaking, entities move in the real world and they always move in the model, there are cases like this where it will be convenient to rethink the system in the model where your resources, which are moving in the real world, are pinned down. So when you're thinking of what a resource is, I don't want you to think, does it move or not? What I want you to think about is it always there or not? So the vacuum cleaner is always in the system, even though it's moving around the room. If we're modeling the room, there's always a vacuum cleaner. Its position just happens to be changing. But the dirt isn't always in the room. At the beginning of the system, there's a lot of dirt in the room. At the end of the system, there's no dirt in the room. We might wonder, how quickly does it take for all the dirt to be vacuumed up? The dirt is the entity because it arrives and departs. Even though it's moving, is the resource because it is always there. Or any questions about that? Does that perspective make sense? Resources are things that are always there, even if they're moving, and entities are things that generally come into existence and maybe change their shape and then have an opportunity to leave. Okay. And that'll become more clear with more examples, I think. Okay. So the other sorts of details here from we talked about last time are state variables and states. So when we talk about systems changing over time, any dynamical system, a system changes over time, is characterized by its state variables. They are the bookkeeping variables that we put in the math or in the computer models to keep track of things that change. So temperature in a fabrication process, that might change. So we're going to create a state variable called T. Number of entities waiting in a queue, that might change. So we'll create a variable for that. Lists are examples of that too. Who is in line right now? That is not a numerical variable, it's a complex data structure, but that data structure changes over time. So we consider it a state variable. Even the clock itself, we consider a state variable. So it's just the things we use to keep track of state. And now, these can be updated every step of the simulation. These might not be updated, but at least should have the potential to be updated. So, you know, listen kind of here, like simulation logic can respond dynamically to these variables as well as change them. So we can actually have an arrival of new entities vary the queue length. And so if you want to simulate bulking, so somebody comes up to a long queue and decides they're not going to get in the queue. Well, so you can actually make the arrival rate depend upon the state variable, which is the number of people in the queue. So it's giving a sort of an example here of different sort of bulking examples here. So, so state variables are the things we'll use inside the computer model to run our logic. So they're the kind of bookkeeping there. And then their values are states. So a state variable might be T, but it takes on the state might be 45 degrees. You know, so it's the actual numerical. So there's a difference between state and state variable. A more important difference is the difference between activity and delay. This is one that usually trips people up initially. An activity is a process duration that you know ahead of time without knowing the state of the system. So I might know that if every time you go through an X-ray machine, it takes an average of 30 seconds to walk through the machine, and maybe there's a bell curve where it generally from 10 to 50 seconds, again, centered roughly on 30. Well, the parameters of that distribution, maybe it's mean and variance, those do not depend on the state of the system. I know those ahead of time before I do any modeling. I can go out with a stopwatch, I can measure that. So that's what I mean by activities. They're things that we can figure out before we run a simulation. That's the key thing there. But there are other things that we have to run the simulation to find out. So if we have that, we know how long it takes to get through the X-ray machine, but we don't know, based on the traffic coming into the X-ray machine, how long it's going to take for people to wait to get into the X-ray machine. So if hardly anybody shows up, then there's not ever a queue and nobody has to wait. You basically go straight into the X-ray machine. But if a bunch of people show up, then you're going to have to wait in line because the people are showing up faster than the people are going through the X-ray machine, and there ends up becoming a queue, and you have to wait for a certain amount of time in that queue. It's not easy for us to predict ahead of time that queue length is going to be without us knowing what the arrival rate's going to be, and many other factors. And so we take all of those things, all of those activities that we know, we put them into the computer model, and we let it go, and then we ask the computer model, of all the entities that we're going through our system, what's the average wait time? And that comes out as a delay. So delays are times that are simulated that you don't really know ahead of time. And you might say, Dr. Pavlic, I could guess that ahead of time. If you just think about it, if you think logically through it, what you end up doing is you're simulating. If you have to do a bunch of math in your head or on the computer to figure out what this delay is based on the information you were given, then that's probably a delay and not an activity. If instead you have to just look up in a book and say, what's the average time it takes to walk through an X-ray machine? Well, that's something that regardless of how many people show up at the X-ray machine, that is always going to be the same. And that's what makes it an activity. All right, so that's like, it's a really important distinction. It's going to be really important for the rest of the semester. So, I know questions may come up about this later. Are there any questions now about this distinction between delays and activities? Does it make sense what I mean, that like we know activities ahead of time? They can be random, but we at least know the parameters of the distribution ahead of time. Whereas delays, we really don't know until we run the simulation. Yeah.
regarding, so if for the time required for a cashier, is that here at like the cashier station?
That's a great question. So when I say the time it takes to pay a cashier, maybe I said that somewhere here, or maybe I said it in class, but that's not referring to the queuing time. It just refers to at the instant you hit the cashier, then at that point, it's going to take me roughly 45 seconds to complete this transaction. Does that make sense? Yeah. That's an awesome question. And that is exactly when we start doing the simulations, when you start taking these measurements, that's going to be really important for you to know what measurements of yours are measurements that are purely related to your resource, the cashier, or what measurements of yours, if you would have set your simulation up different, would have changed, like the arrival rates and so on and so forth. And so if I say the total time in the system is a combination of activities and delays. The amount of time you spend waiting in a queue is all delay. The amount of time you spend waiting at a cashier, working with a cashier, is all activity. Any other questions? Thank you for that question. That was a great question. Questions online? So activities may be variable, but their statistics will be known. A delay for one entity is often the accumulation of activities generated by other entities. So the same thing I kind of just said there. All right, so this is still just review of what we were talking about from last time. The other important thing here is I've already started talking about randomness, and so we need to sort of be formal about what we're doing with randomness and why we're even talking about randomness. And the point here is that we want to build models that capture realistic variation, but it's important for us to go through figuring out all of the millions of details that are actually responsible for generating the variation of real life and replacing them with a probabilistic distribution that does a lot of the work for us in a pretty realistic way. So instead of having to know 1,000 parameters that I have to fix by measuring a bunch of different things, if I really were to say about it and say, well, you know what, actually, if I look at the inter-arrival times of people arriving to an airport, if I were to histogram those, and they look pretty much like an exponential distribution, well, an exponential distribution has one parameter. So with one parameter, which is sort of the average rate of arrival, I get the entire exponential distribution. And so I go from all of the realistic details that generate the real variation to only needing a single parameter to generate simulations which have the same distribution as real life. And we can talk about why exponentials are so good at modeling one thing and normals are so good at modeling another thing. In fact, we'll get to that. But the basic idea here is what I'm trying to communicate is that there are distributions that tend to be good models for realistic systems that do not need to know all of the details of the realistic system. They only need to know one or two parameters in order to capture the same distribution. And that idea of using randomness as a source of variation in a model is what we refer to as stochastic modeling. So stochastic means guess or conjecture. I'm making the conjecture or the guess that I can use a random model, even if the real world system isn't random. So we're not simulating quantum mechanical systems or anything like that. We're simulating real, deterministic, boring, mystical systems, but we take the guess that we can use randomness as a source of variation instead of trying to generate all those ugly details in the computer. And we can get pretty darn close and maybe actually have a more generalizable model that works across a wide range of systems. And so that's the reason we do that. So the randomness is only for modeling. The choice of input modeling is the choice of those probabilistic distributions. Like I mentioned, that maybe for inter-arrival times, distribution. Maybe for the time it takes to make a subway sub at Subway, we'll use a normal distribution. And there's a central limit theorem explanation for why we would use the normal distribution for the time it takes to make a sub. And there's another explanation for why we'd use an exponential distribution for the time in between people here. And we'll get into that. But so certain distributions are better matches for certain processes in real life, but the processes in real life are not random, but we're going to assume that they're random to make the modeling task easier. That's stochastic modeling. Oh, that's all I'm saying here. Simplifies. Challenge here is that we need to make sure that in order for our outputs to have similar variability, well, the challenge here is that our outputs, our sims, whenever we hit run, are going to give us a different answer. So now we're going to run experiments in the computer that are just as variable as experiments in the real world. Well, we now know that if I were going to implement something in the real world, couldn't just run it once. I'd have to take multiple samples to see if my intervention actually made a difference, because I might have just got lucky with the first look. Same thing inside here is that when we run our computer models, their outputs are going to vary every time we run them. And so that means we're going to have to run them multiple times. So the advantage of a purely deterministic approach, a more mathematical approach, is you only have to solve the equation once and it's done. The disadvantage here is that we have to run our simulation models multiple times and take statistics over those runs in order to make sense of them. And so in some ways, our simulation models inherit that ugly property of real world systems. And that's what we'll learn how to do as well. Okay, just kind of to summarize all of that and kind of a picture here, the only way we get output variation that's realistic in a real world or in a simulation is if we have proper input variation. And so the choices of inputs, that's what we refer to as input modeling. So you can say, well, how the heck, when I hit run on my simulation, do I get a different output every time? Well, it's because your inputs, like the time in between arrivals of a customer, has been random to your simulation. So because we put randomness into our simulation, we get randomness out of our simulation. And we want randomness out of our simulation. And so the challenge will be figuring out the right randomness to put into our simulation to make that work. And that is all about how do we choose realistic input models to get realistic outputs. And if we choose the wrong ones, then we won't get the right outputs. And so this is the so-called garbage in, garbage out property. Regardless of how great your simulation model is, if you choose the wrong input models, you'll get the wrong outputs. And you'll print out the flow chart. Somebody will say, this captures everything that goes on at this factory. But what's hidden underneath the flow chart is you might have chosen bad models. And so the good results that you get here may actually be a poor representation of how this is going to actually behave in real life. So we really need to make sure that our input models match reality so that our outputs will match a hypothetical reality. And that's input modeling. Okay. And that's all I'm sort of saying here. So any questions about that? That's all the summary of where we've been so far. Discrete event system simulation, stochastic modeling, and so on. Questions online? Okay. All right, so now we've got this new step here. How do we hand simulate these discrete event system simulation models? This is part 2 of your homework. This is pretty much lab 2 as well. And so how do we, this is weird that I'm saying that time jumps from event to event. It does not flow. Time for us in our real experience flows. So how do we simulate time that does these jumps? So we're going to use what's called the event scheduling worldview. And so we're going to see here that every time we process an event, we're going to take an opportunity to schedule a new event in the future. And if we keep a calendar of all of these events, we can just jump to the next thing in the calendar, and that's how the simulation runs. So events, again, are points in time where the state of the system changes, and we jump from event to event, irregular jumps, skipping everything in between. And we're going to maintain, again, what I call an event calendar, which is going to keep track of all of the events ahead of us. And so every time we process one event, we're going to say, is there a new event we need to schedule in the future based on the process logic we know now? And then once we're done processing this event, we just look at the calendar and say, what's the next event to jump to? And then we jump to that, skipping everything in between. It's like looking at a real calendar. If you have nothing on your calendar from Monday to Wednesday, then we're just assuming that we skip Tuesday and just go directly to Wednesday. And that for the computer makes the sims a lot faster than trying to simulate a bunch of time where nothing's at each event, we're going to update our clock to the next event in the calendar. Then we're going to execute the logic at that event in the calendar, and then we're going to schedule new events into the calendar for the future. We'll see an example of how we do that. So the event calendar, how is that modeled or how is that represented in the computer? It is an ordered list of events. So this is sometimes known as a priority queue. So it is a queue, which means that it doesn't have a first in, first out flavor here. It does sort of in terms of time. So it's like a data structure, a queue, where when you add things in, everything you add in has a time, and at the instant you add it, it always will get sorted into the right time. So when you then dequeue something off the queue, you're always going to get the next thing in time order. So that's what the idea here. The book will call this a future event list. I think sometimes will just be called an event list. Some other resources may just call it a schedule. So depending on what tool you're using, Arena, Flexin, Simio, Simulink, and Mab, they all might use different terms for it, but it's all the same: event calendar, event list, future event list, or schedule. And so the two fundamental operations here, we can get the next item in terms of time order, and we can insert an item having faith that it will be inserted in time order properly. So we as programmers have access to the event calendar, but our simulation does. So at no point do you want your logic to try to look ahead and say, oh, it looks like we've got 4 arrivals up, so I'm commission additional resources for this machine here. Like you don't want to say, like, well, let's say for a clerk in a bank or whatever, you don't want to look into the future and say, well, because I've got 4 customers coming and I only have 1 clerk now, I should add additional clerks based on what's in the event calendar. That would be like in real life looking into the future, which we can't do. So this event calendar is so the computer can simulate. It is not for your process logic. You as a programmer can look at the event calendar, bug your code, but you should not in your code write anything that references the event calendar, because the event calendar is off limits. It is not a state variable. Hopefully that makes sense, or hopefully will make sense as we go through these examples. All right, so here's a simple example of this, similar to what you'll do in your homework. So this is a little more graphical. Imagine if I'm modeling a car wash, and the car wash has got 2 resources in it. It's got the actual car wash, and it's got a vacuum station. These are 2 resources that only one car wash at a time, only 1 car can go into the vacuum station at a time. Cars arrive, they then travel to the car wash. So there's a travel time we have to worry about. They then travel to the vacuum station, travel time we have to worry about, and then they leave. And there could be multiple types of entities. There could be, a little economy car or something, or there could be sports cars or something like that. So, so these are the types of things we could think about modeling if we're modeling a car wash. Now, if I were to run this model of the car wash, I could look at all of the events and it would form a timeline that looks like this. So over the entire sim, I got car A arrives, it enters the wash. While it's in the wash, B arrives, but B can't, it travels to the wash here, but it can't get into the wash because A is still in it. So then A finally exits the wash, which will correspond to B entering the wash. A travels to the vacuum, it enters the vacuum. While it's vacuuming, car B finishes its wash, and so on. So we can see that these 2 cars are competing for these 2 resources, and whenever one of them is in the other one has to wait. And so we're simulating, trying to figure out how much these cars have to wait. So how would we generate that timeline ahead of time? Well, we know that car A arrives first. So before this schedule is built, so this is the process of building that schedule. This is what goes on inside the computer, which you'll do by hand in the lab 2 and in this first homework. And then after that, you're not ever gonna have to do it by hand again, because the computer will do it for you. But we need to sort of know what the computer's doing, so we're gonna start doing it by hand. So always the beginning of time is that car A arrives first. And so we're gonna schedule that event that car A arrives. at a particular time, and we're going to jump to that event. This is time 0, where car A arrives. Now, when we jump to that event, we have to say, well, on an arrival event, what do we know must happen in the future? Well, if A arrived, it now is going to drive to the car wash. That's an activity. We know roughly how long it takes for a car to get car wash, the entry to the car wash to the actual car wash station. And so we can figure out how much that time is and schedule that. That will be something we know is going to happen in the future. And the other thing that we know is that after car A arrives, car B will eventually arrive. So the time between car A and car B, that comes from a distribution. We know on average, it takes whatever, 5 minutes between every car. So we can draw from a distribution that has an average of 5, and we can figure out that time, that difference between A and B. Those are the that we know must happen in the future right after car A arrives. And that's all we know. So that's all that we're going to worry about scheduling. So at that point, we can get rid of that event and jump to the next thing in the event calendar. The next thing in the event calendar happens to be an event that we just scheduled, but we didn't know it was going to be that. It could have been anything. It could be an event we scheduled many, many steps ago. But in this case, it happens to be the one that we just scheduled. So we are going to go to that event, and then we have to ask ourselves when we jump at, what are all the things that could happen when car A enters the wash that would result in us scheduling things that will definitely happen in the future? Well, when car A enters the wash, what's definitely going to happen sometime in the future? Anybody? It's going to exit the wash. It will eventually exit the wash. And so we schedule that ahead of time. We can draw from a distribution. How long does it take to usually get through these washes? And based on the quality control of how well this wash process was built, that may be a very, very narrow variance where they only take exactly 40 seconds, or maybe variance based on the weight of the car or whatever. But we could draw from that, and we could figure out that difference between here and there. So we know car A is going to exit the wash eventually there. And then we have to ask, is there anything else that we know is going to happen? And we don't. All we know here is that car A has started to use a resource. It's not, if it gave up a resource, then we know that something else could start using it. But at this point, there's nothing else we can schedule. So we jump to the next event. At this point, we know that car A has arrived here, or arrived here. And so what we can do at this point is we can schedule what's the only thing we know that's definitely going to happen. Well, we know that it will drive up to the busy car wash station. So we can schedule when it will be ready to enter the wash. But we don't know when it's going to get out of the wash because car A hasn't got out of the wash yet. So that's all we can schedule. You might say, but Ted, but Dr. Pavlic, I know that car B is going to enter the wash here when A exits the wash. So why don't I just schedule ahead? Why don't I say car B a certain amount of time? So let's go ahead and schedule when car B exits the wash. Just do it now, get it out of the way. But that is doing the simulation in your head. Like that is going ahead of like all the computer is going to know how to do is one step at a time. And we're going to get complex systems that have parallel processes coming into them where it will not be so obvious that, like here, it's pretty obvious that when car A exits the wash, B is going to enter the wash. But there might be some preemptive stuff that's going to go on here. There might be other things that happen. So that's why we only really can schedule the thing that are 100% confident, and we let the other things happen when they happen. So we'll just wait until we get to car A exit the wash. If B is still waiting for the wash, then we'll schedule B's exit to the wash. So do not schedule a bunch of times ahead. Only schedule sort of the next immediate thing. So the only thing, we know that car B will be ready here. Car C, which I haven't brought up here, but if there is a car C, we also can schedule when car C arrives. And so that would be the only other thing that we would schedule. And then we jump ahead. We say, well, what's the next event in the event calendar? Well, car B being ready to wash. Well, car B is just sitting there waiting. So there's not really anything we can do because we can't, the system state does not change. And if the system state does not change, then there's probably no reason to schedule another event. So we can just, well, effectively be able to jump to the next point here, and that we're jumping over our first delay. So the time here to there, all the other durations I've talked about so far have been activities because we could draw them from a distribution we knew ahead of time. This red duration between car A exit wash, we got that from doing the simulation. That is an output of the simulation, and that's what makes it a delay. Is that clear? Are there questions about that? Why this is a delay and why every other duration so far has been an activity? These are the things that we want to accumulate over time, will tell us about how well our system is performing. Because if we've got a good performing system, we've minimized delays. If we have a bad performing system, everything's always waiting on everything else. All right, so what we can do here, since B is waiting, we can then we can formally add it to a state variable, which just keeps track of how many cars are in the queue for the wash resource. That's all I'm sort of modeling here. So I'm going to put them in this line, this waiting line, and that will relate to what you're doing in both the homework and the lab. You'll see something like that. And then we jump to when car A exits the wash. So car A exits the wash. For an instant, the state of the system changes. The wash becomes free. So we'll deal with that. That means we can put B into the wash, but we need to also deal with what happens with A. And so we can schedule the time it takes for A to get to the vacuum. That's one thing we can schedule. The other thing is we now can schedule that B, well, we can see B, which was sitting in the queue, is now out of the queue in the wash. And because B has entered the wash, we can schedule when B exits the wash. And then we can keep jumping ahead. And so we keep doing that again. So car enters the vacuum, we then would schedule when car A exits the vacuum, and so on and so forth. And so that's how we build up this schedule. So if all I know is I have a distribution of inter-arrival time and a distribution of service times for this resource and this resource, then I can generate this timeline going step by step by step. And that's what the computer will do when it's doing these DES models. So are there questions about this? On Thursday, we'll actually walk through seeing this in tabular format, which will be the format that you'll answer on your homework, and the format that you'll see also in lab 2. But I'm just showing it visually here. So I'm not ever going to ask you to draw one of these timelines. These are just something I put up there as an attempt to illustrate the event calendar. But normally when we talk about the event calendar, we're going to write it out in tabular format, which we'll see again on Thursday. So questions about that? I see a question online. So question online is a good question. In the assignment, let's say homework, will we have to pool and calculate distributions, or is it just explained the setup and the reasoning behind it? So in the homework assignment, if you haven't looked at it already, I will give you all of the inter-arrival times and all of the service times in a list. Grab the next one in the list as you need it. And that'll be explained in the homework. And that's also going to be explained in the lab. So we haven't sort of taught you how to draw random numbers in from distributions that we want yet. And so we're going to forget about the random number stuff until we get there. And in the meantime, I'm just going to give you strings of numbers, like the inter-arrival time between these two cars will be 5. The inter-arrival time between this car and car C will be 2, and so on and so forth. I'll just give you all of those numbers, and you'll just grab the next one from the list. All right, any other questions? Looks like that answered that. All right, so like I said, so this is exactly what I was just saying. Inter-arrival times and service times, I'm going to provide you in list format. But as we get away from this, a little bit later before the midterm, we're going to start drawing them randomly so that they don't always have to be pre-drawn ahead of time. Other little things, and this is almost kind of premature for me to bring this up now, but this will make more sense when we get into actually doing the arena. But there are bunch of practical issues in timing an arena that you need to watch out for. Units are a big deal. In different parts of arena, you can specify different time units. And so you want to make sure that you're always using the right unit. The other thing is that inside the computer, if you're simulating things that happen really, really, really frequently, you can get round-off error issues where a bunch of things that should have happened within a second of each other get spaced out over multiple seconds because of round-off error in the computer. It's going to be more like milliseconds or nanoseconds than seconds, but these are things too, that these computers are infinite precision. So if you want to schedule events that happen right on top of each other, it can create problems. Now, you might say, well, if a bunch of events happen right on top of each other and otherwise are spaced out, maybe all of those events that happen right on top of each other, you could just call one event. So there are other ways that we can model that, and those things will come up later in the semester. All right, questions about the timing stuff. The timing stuff will be the hardest thing to learn at this point in the course before we move on to that. So that the hand translations will be things that will be the most complex. But again, I'm always available if you need to contact me. The TA is available. There's video resources online. There's examples that I've done online. The samples you can download. So all that's available to get you used to that. All right, so the other couple things I want to comment or prep us for here is, so the generic simulation steps that we will then do an example of on Thursday. So initially, we're always going to start on our first arrival at time 0. We are always going to schedule an end event. If we say ahead of time, as we do in the homework, that the simulation ends after 45 time units, 45 seconds, 45 minutes, or whatever, then we schedule an end event, which is a fictitious event that just tells the computer or you to stop simulating. So those are the first two things we always do, is the first arrival and the end event, and then we continuously process whatever's in front of us, which in this case will be that first arrival. Then in these simple queuing systems, like we've seen in the homework, then we've got on our every arrival event, you go through this same logic. And that logic is written out here. We move our clock forward to the arrival event. If the resource is available, we move the entity into the resource and reduce the number of resources available. We can determine how long the entity will be in that resource by drawing a service time. And we created a departure event based on that service time, which is basically going to be now plus the service time. And we schedule that event. If the server is not available, we add the entity to a queue. It's just like a list, which says everybody who's waiting for the resource, and we move on. We can determine the next arrival time by drawing from the inter-arrival distribution and schedule that. And then we can, and that's what I'm saying, create an arrival thing. And then if there's any stats that we need to collect, like for example, we might want to know how long the queue is at every time period so that later we can say, how long did the queue get? What was the maximum queue length? And this allows us to collect those stats so we can do that maximum length calculation later. So we do that for every single arrival event. If we happen to hit a departure event, we always do this. We always move clock forward. That's our common thing. If the queue is not empty, then this departure event is effectively allows for another entity to move in to the resource. So move that resource, that entity that's been waiting, into the server, draw its service time, schedule the departure time based on that service time, and then again, update statistics. And so if we, that entity that moved in, we can see how long was that entity waiting, and we could then update a statistic. What is the maximum amount of time that an entity has waited to enter this resource? And we could update that here. And then finally, on an end event, if we hit to that end event, we just move clock forward to that time, update statistics, and terminate. So in your homework, you don't even have to write a separate line for the end event. You can just show me the line right before the end event and just assume that at the instant you hit the end event, the sim stopped. And those are the three sort of steps. So every single time we hit those, we run through that logic there. So we've got the arrival logic, the departure logic, the end logic. As we move through there, we just go and we do that same. So it becomes very over time. There's state variables that we're commonly going to use in these systems. We might keep track of whether a server is busy or idle. We might keep track of how many entities are in the server. We might keep track of how many entities are waiting in the queue. And we need to update these at the end of those events. So whenever there's a departure, we need to update these. Whenever there's an arrival, we need to update these, and so on. We also usually keep track of the arrival time for entities, so we know how long they've been in the system. We might also keep track of when they arrived at certain resources, so we can see how long did they wait for a resource, how long did they spend in the system after that resource, and so on. So those are things that you'll see these. You'll definitely see LS, LQ, and arrival time in your homework. You'll have to update those as you move through the sim. So in the next lecture, we're going to do these in a hand simulation example that will be very similar to your homework B1. But meanwhile, you'll get some experience with this in lab 2, and if you're starting to work on lab or homework B1 yourself. All right, so any questions about the sim steps? So I just want to make a couple more comments about output measurements, and that's all that we'll do today. All right, like I said, the sim steps are going to be the hardest thing to get used to, but once you get practice at it, it'll become very automatic and easy to do, and then you'll be happy to hand it off to a computer to do it for you. Okay. All right, so last thing I want to comment here is that there's, at the end of these sims, there's a bunch of different performance measures that we can take. And so, Gesundheit. So, you know, and just like in a real system, you got your PIs, your computers, and so on. We define performance for these simulated systems in exactly the same way. So we're usually going to think about performance variables as in either be from an entity perspective, or from a queue perspective, or from a resource perspective. And we often will talk, you know, gather statistics on all three of those. What I mean by that is, like, grouped by entity here, I can, after a simulation runs, I can ask how many entities made it through the sim. So what's the total production? Or I can say, of all the entities that made it sim, what is the average amount of time they spent in the sim, which includes the time they spent in servers, as well as waiting for servers. And so I'm just adding up. If TS is the total time part I spent in the system, I'm just going to add up all of their times, divide by the total number of parts, and that's my average time here. Or I can calculate the maximum time. Of all the parts, what's the one sucker part that had to spend the longest amount of time in the system? So these are all the kind of grouped or aggregated over the entities, not worrying about where they were in the system. The other thing we think about is, what about queues? And so a lot of times we don't care about the entities, we care about particular choke points in our system. And those might be, you know, those might be characterized by the queues. And so we can say, for this particular server, I had a certain queue associated with it of all of the parts going to that queue. I don't care what type of part they were, what type of entity they were, how long did they spend waiting in that queue? And I could take the maximum waiting time in that queue. Or I could take the average waiting time for this queue. I don't care what type of part it was, whichever arrived in this queue, if I aggregate over all of the ones in that queue, what is the average waiting time? The other thing I could get is length characteristics. So across all of the simulation time, how long did the queue get on, what was the maximum length for this simulation run? Or the time average queue length. So this is a little bit more complex here, but it's, instead of taking the sort of a max, or it's kind of an average, but it's an average over continuous time. So if I take the queue length, which is you know, an integer that moves around over time, I can take the area underneath that curve, and I can divide that area by the total time that I'm integrating over. And that sort of gives me a time average, where if the queue length is always 0, it'll be 0. If the queue length was always 1, then this will be 1. But it allows me to sort of say, you know, I can have, this is what you might mean when you say we have an average queue length of 1.75. Well, that sort of means that that sometimes the queue was 2, sometimes it was 1, but it was more often than 2 than 1. That's what the 1.75 would be. And that's what we mean by time average, is that it's a continuous average. It's not a discrete average. Like this here is a discrete average here, where we're dividing by an integer, whereas here we're actually taking an integral and normalizing. The other resources that we're going to, so the other outputs we're going to get here are utilization metrics, which have to do with how often is this resource being used. And the simplest metric we can get at a state variable level is sort of, we might use the term B, 1 for this server if it's busy, 0 if it's otherwise. And then we can take the time average. And so this will end up being a fraction. So if this comes out to like 25% or something like that, then that would mean 25% of the time this server was busy. Now we can generalize this notion of utilization, instantaneous utilization, this thing here, to resources that have a larger capacity, in which case we do the fraction of their total capacity. So if there's 5 clerks, that'd be the denominator. If there's 2 clerks currently being used, then it's 2 over 5 would be the instant number that would end up going into this integral to calculate the utilization over the whole sim. So those are sort of the 3 categories of the output metrics that you're going to see over and over and over again. Now, of course, you can create your own output metrics, and you'll have a need for doing that. You'll have people who have a stake in your system that are going to care about things that maybe don't fit these conventional frames here. And so you may have to come up with your own, and that might require you in your simulation logic to take other data. But the nice thing about these is that generally all of these here, the menu, Arena already calculates for you. So Arena knows that these are so commonly used that when you run a sim, it's going to have a report, which will report on all of these for you, so that you don't have to do all of that extra legwork. But if you do need something more than this, then Arena also provides you the ability to do that, but it's just going to take a little bit extra logic you have to manually implement. All right, so any questions about these output metrics, these definitions? And hopefully a lot of these will be terms you've seen before in quality classes, whatever else. We're going to see them again, but instead of measuring them on real systems, we measure them on simulated systems to compare to real systems. Okay, so as an example of that, and some questions online. So as a final example of that, so what's an example of how we could make use of all of this combined together? Well, if we consider a really simple problem, let's say I have a server, let's say it's a drill press, and I've got a bunch of parts coming into the drill press and they queue up when the drill press is not available. And I want to know what would be the effect on this system if I doubled the arrival rate. So what would certain performance metrics, how would they change if I doubled the arrival rate here? So I run a sim, and some of these, this is from on the projector here, it's a little pixelated, but on the PDF, you can maybe read a little bit more, but I can sort of say, like, up here, I've got a total production plot. So it's total production, and down here, it's plotted so that the performance is going horizontally. So this is a production of 0 is on the left, a production of 10 parts is on the right, and a production of 5 parts here is right in the middle. The open squares are the baseline arrival rate, and the open triangles, which are also on the bottom here, are the doubled arrival rate. And the first symbol, so the filled symbol here, that is the first replicate of our simulation. So we ran 5 simulations at the baseline arrival rate, and that gave us the top data here. 5 simulations at the doubled arrival rate, and that gave this bottom one here. This was the first simulation at the baseline. This is the first simulation at the double arrival rate. And what we see here, if we just look at total production, is the variance is hugely overlapped. Like if I were to just look at the first sim and this first sim, I would see there's a slight increase from first sim to first sim as I double the arrival rate. But if I then look across all of these sims here, then it's not a very clear out. It doesn't really look like I'm actually producing a whole lot more, though my arrival rate has increased. So it's hard for me to compare these two. If I look at waiting time in queue, there's some interesting other things going on here where it looks like maybe the waiting time in queue is increased, but if it wasn't for this first simulation run, then all of these are pretty much overlapping with these ones here. So the point I'm here, I can go down through here, average time in system, total number of parts in the queue, drill press utilization. I mean, there may be differences from these two treatments, baseline and doubled arrival rate. But if I'm just looking at the random outputs, I don't actually say anything about that, because really it might just be that that the differences that I see here are just due to random chance. That maybe for this one, average time in system, that maybe this triangular one here, it looks like it's in there really a long time, but maybe it just was an unlucky run where the arrivals just all landed right on top of each other. And so that's the reason why there was extra queuing and those spending extra time in the system, because most of the typical runs are really right on top of the baseline arrival rate. So maybe there may not be much of a difference here. So this is what we have to contend with, is that when we run these things, it's not going to be very clear what the difference between our two treatments are if we just look at the outputs of, say, 5 runs. Now, we're going to learn that we could run 500 runs. And maybe if we ran 500 runs of both, then these two distributions would start to separate and we could start seeing differences there. But what we're, so the high variability is going to affect this, but hopefully we're going to say, well, you know, every time I ran the sim, it took maybe 10 minutes for the simulation to run. I don't want to run 500 of those if each one of them takes 10 minutes. So that's the reason we're going to turn out of like 380 and 385. That's where we're going to resort to saying, well, is there a way for us to compare the mean of two populations when I only have a small number of samples from those two populations? Well, there is. What is that test? What is the statistical test for comparing two means from populations that have been very lightly sampled? I heard it over here. Starts with a letter. I'll wait and see if I hear it again. Starts with the letter of my first name. T-test. So this is an example of where we could use a t-test to be able to say, I can't tell a visual difference between this and that. Can I make a rigorous comparison between these 5 outputs and these 5 outputs? And if that t-test turns up with a p less than 0.05, then I can say there's a difference between these two treatments. If there's not a difference, that might mean I need to take more data in order to quantify the difference if it exists. But that's why we're going to start figuring out how to use these statistical tools to make sense of the variance in these outputs. That's where we're going from here. All right, so any questions about that? And so the stats is going to start trickling in as we get closer to the midterm, and pretty much well after the midterm. The probability and the modeling is kind of everything before the midterm. All right, with that, that's all I got for you today. So let's do an attendance exercise, just the one for today. And I will put this in the chat as well. So the question I have for you, if I can get my mouse back, I'll just put it in this chat. So the question I have for you for this, all right, that'll be, all right, there we go. So the, let's ask the question, what is the name of the simulation what is the name of what we call in a simulation that represents the things that do not leave a system? So what are the things that so what is the name of the type of simulation element that always stays in a simulation in the system and never moves and never arrives and never departs? It's always there. It's the thing that's slowing everything else down. It's the thing that's limited. What's the name for the limiting thing in a simulation? Is it an entity? Is it a resource? Is it an attribute? Is it an arrival, or is it an activity? Is it a delay? What is it? So that's the question. So fill that out, submit it, and that's all I've got for you, and I'll see you Thursday. And lab 2 is released tomorrow, but you're free to work on it today. It's the name of the element, the simulation that never leaves the simulation. All right, any questions online? If not, then I'll go ahead and end the sim. Give me 1 second to close the Zoom out here. It's on the calendar. It's sometime in October. Sure, just give me 1 second to yes.